SwayamPrabha. Digital India. Educated India.
Hello, in the past few lectures we have been looking at kinematics. Starting with this lecture today, we are going to start on particle kinetics. To give you an overview of what we are going to discuss in this lecture, we are going to introduce Newton's laws of motion. We are going to discuss what follows from these laws, the equation of motion, and we are going to look at some applications through some examples. Now, we are not going to discuss the Newton's laws of motion as written by Newton in his book Principia, the most famous book possibly written by any scientist, but we are going to interpret or understand these laws in the framework of how we understand them today. In today's context, how we interpret or explain those laws. The first law says that a particle persists to be in a state of rest or uniform rectilinear motion unless acted upon by an external force. Now, Newton's first law, the word force is not present, it is called agent or action, but here in the present context in modern science or modern physics, we understand this law in terms of absence of force or a particle motion in absence of any external force. Now, this law defines what is called an inertial frame. The first law defines an inertial frame. This is a very important starting point for kinetics. If I show you a video in which you see some object kept on a table, and suddenly in the video you are seeing that the object starts moving, and there is no trickery, the object is really moving, not by somebody pulling an invisible string or some magnetic force, no, it is moving. What will be your conclusion? That the particle is moving without force? Then it defies the first law, then that frame cannot be an inertial frame. Now, how can this happen? Suppose this camera is mounted on a moving coach, a railway coach, let us say, and the train was moving at a constant speed. Suddenly there is a braking, a tremendous braking. What will happen? All the objects will start shifting towards the direction of the motion of the train, or opposite to the direction of acceleration. When it is braking, the acceleration is towards the reverse, backwards. Therefore, the objects move in the direction opposite to that acceleration, or what is called deceleration, right. Therefore, an accelerating frame is a non-inertial frame. Newton's laws cannot be, in the form that we are going to present, cannot be applied to objects in a non-inertial frame. We have also seen that a rotating frame is a non-inertial frame. So, accelerating frame, rotating frame, you cannot directly apply Newton's laws. The first law forbids, so you must use an inertial frame to represent all rates, then of course you can do, and we are going to demonstrate that. So, the first law is a very important law which defines what is an inertial frame. The second law is actually the useful, the working equation of motion, which gives us the equation of motion of a particle. The rate of change of momentum of a particle. Now, in Newton's law in Principia, I mean the momentum is not there. So, but in the present day context, we will talk about rate of change of momentum of a particle. The rate of change of momentum of a particle is equal to the net external force acting upon it. This defines the kinetics of motion. This is something like a constitutive relation between force and motion. I will talk more about it as we proceed. So, this law gives us the working equation for and allows us to develop the equation of motion, what is known as the equation of motion of a particle. The third law, which says to every action, now this is action, Newton used action in place of force. Every action there is an equal and opposite reaction. This leads us to the concept of the free body diagram. Of course, this law, the third law, also has implications for momentum conservation that we will see later on, but this law is very useful in understanding or developing what is known as free body diagram of a body, which is of a system which is composed of multiple bodies. Therefore, the third law leads us to the concept of free body diagram, which is very important in Newtonian mechanics. Thus, these three laws are a complete recipe for deriving the equations of motion or studying dynamics of a particle. This is a complete recipe. It gives you the frame of reference, it gives you the equation of motion, and it allows you to develop these equations of motion particle wise. Suppose the system is composed of multiple particles, what allows us to cut connections and draw free body diagrams, so that we can finally write the equations of motion. So, that is given by the third law. Now, kinetics, when we discuss of kinetics, therefore, it must have these four, I mean these laws in every respect, these laws must be taken care of. Choice of coordinate system. First of all, I mean the first thing that we do in any study of mechanics is fix up a coordinate frame. Most of the time the coordinate frame is for geometrical convenience. Otherwise, every problem can be solved theoretically, every problem can be solved in, let us say, Cartesian coordinate frame. Equations might look very difficult, but that is not an issue, you can solve it. So, if a particle is moving on a circular path, we will use polar coordinates, but that is because it is convenient to use. You can always do it in Cartesian coordinates. So, we have a choice of coordinates. Then comes the step of free body diagram. So, I am now giving you the steps that are required to derive the equation of motion. First is coordinate system. You choose a convenient coordinate system in which the geometry or the kinematics is convenient. Then you draw the free body diagrams, isolate the particles. If this is a system of multiple particles, isolate the particles and use the Newton's third law to draw the free body diagram. Develop the kinematics. This was the step we were discussing in the previous lectures. So, basically represent the acceleration as seen by an inertial observer in terms of any frame that you might have chosen to solve the problem in. This part is actually the trickiest, the most difficult part. Kinematics is the most difficult part. Actually, kinetics is usually a very straightforward step. Develop the kinematics of the particle or the particles, then write down the equation of motion using second law for each particle, and then you need to combine. Now, this is the form, this is the equation, I mean this is the form of Newton's second law that we typically use. Rate of change of momentum, time rate of change of momentum is force. The left hand side of this equation the origin of the left hand side of this equation is purely kinematic. It involves geometry. The right hand side of this equation, of this law, is kinetic in nature, that is, it involves force. Thus, Newton's second law is kind of a constitutive model or constitutive relation for dynamics of a particle. Just like you have Hooke's law. What does it relate? It relates stress and strain. Strain is a kinematic thing. It is related to the geometry. Stress is related to the kinetic part, its force, born out of or developed because of force. And Hooke's law is a constitutive relation of a material. It represents the constitutive relation of a material under forcing and deformation. Similarly, Newton's second law, this form, is a connection between the kinematic or the geometric variables and the kinetic or the force variables. And you know that P is what is called the linear momentum, is mass times velocity. When the mass is constant, that is dm dt is 0, then it leads us to the familiar form of Newton's second law, which is ma is equals to f. Now, this is a vector relation, again and again I am repeating this, it is a vector relation, can be used in any frame as long as the kinematics, that means the left hand side, has been represented for an inertial observer. You can choose any frame. Let us start with the most classical example, the pendulum, which should be discussed in any dynamics course, or which is discussed in any dynamics course. Let us start with that. We will derive the equation of motion of the mathematical pendulum in a uniform gravitational field and determine the tension in the string. So, the mass of the pendulum is m, length of the string is L, and here I have shown the angle theta, and it is in a uniform gravitational field with acceleration due to gravity as g. First step, fix the coordinate system. I choose to use the polar coordinates. I will show you, just after this I will show you a working in a different coordinate system. Okay. Here we have the polar coordinate system represented by ER cap and E theta cap. Remember, always check this, ER is the direction of increasing radial distance, though here does not, but we have to be careful about the direction of ER. E theta is in the direction of increasing theta, that is how I have chosen E theta cap. Free body diagram, second step. In the free body diagram, I draw the mass points separately. Every mass point must have a separate free body diagram. Make it a point to follow this. Here there is only that pendulum mass, single point mass. I have drawn the free body diagram. One is the weight because of the gravity and the other is the tension. Third step, kinematics. Kinematics as seen by an inertial observer. This we have derived. Acceleration in the plane polar coordinates is r double dot plus minus r theta dot square. This is in the direction of radial coordinate ER cap plus r theta double dot plus 2r dot theta dot in E theta cap direction. But now, because this is a pendulum with fixed length inextensible string, therefore r double dot is 0, r dot is 0. So, those terms I have dropped out, and therefore, my expression of acceleration represented in a rotating frame, but as seen by an inertial observer is this, represented in the rotating frame ER E theta cap, but this is what is observed by an inertial observer. Equation of motion is a vector equation. I can use any frame. So, here I have chosen plane polar. So, I have to represent all vectors in plane polar coordinates. Acceleration I have already represented, force I have to. This is the left hand side, straightforward. We have taken the acceleration expression. Force in the plane polar coordinates, here the tension vector is in the direction of minus ER cap. So, I have written that first term is the tension vector minus T ER cap. The second is mg as represented in this plane polar coordinates. So, mg is this way, and see this angle is theta. Therefore, mg cos theta in ER direction and minus sin theta in E theta cap direction. So, this is an important step representing the force itself in the coordinate system that we have chosen. Now, what remains is to rearrange and look at coefficients of ER and E theta. This is the equation that follows if you match ER coefficients from both sides. On the left hand side it is minus ml theta dot square. That minus I have cancelled out, I have made a simplifying step, I have changed reversed all signs. The second equation follows from E theta. Therefore, this is from ER cap and the second equation is from E theta cap. The first equation leads me to the expression of tension in the string. The second equation leads me to the equation of motion, which I have again simplified, and this you will recognize as the equation of motion of a pendulum. We have followed all 4 steps. I have demonstrated by following all 4 steps. First is fixing coordinate system, second is drawing free body diagram, third is writing the kinematics as seen by the inertial observer, and then equation of motion. What we had, the unknowns in these 2 equations of motion, if you notice, so these are the equations that we have obtained. There were 2 unknowns, theta and t, and we had 2 equations, so we can solve. T is a part of the solution, the force is a part of the solution in Newtonian dynamics. Equation of motion, of course, we have derived, but the internal forces are also part of the solution in Newtonian dynamics. Now, let us switch to a different coordinate system. Now, I will demonstrate the same problem done in Cartesian coordinate system x y. The figure is shown. I have drawn the free body diagram. So, first 2 steps are over. Kinematics is straightforward. Acceleration in Cartesian coordinates is a non-rotating frame. So, x double dot I cap plus y double dot j cap. So, I just write it directly in my equation of motion, and on the right hand side forces represented in x y. mg is in j cap direction, j cap you should notice that y axis is taken downwards, x axis is taken to the right. You can reverse and redo the problem. So, mg j cap, that is the weight acting downwards, and tension from the free body diagram, look at the tension, it is minus sin theta. So, T is the magnitude times the unit vector direction in that direction, tension vector direction is minus sin theta I cap minus cos theta j cap. Compare the coefficients of I cap and j cap. This is I cap, this is the j cap equation, this is what you have. From the first equation I write x double dot as minus t by m x by L. Why? Because sin theta, I have used that sin theta, remember, but theta was not our variable, theta was not our variable, our variables are x and y, our coordinates are x and y, theta is not our coordinate. Therefore, I must replace that sin theta with in terms of x and y, sin theta and cos theta. So, sin theta is x by L, that you can see very easily. Sin theta is x over L, cos theta is y over L, that is what I have done in this step. So, here I have the equations of motion. Now, here you will notice how many unknowns? X, y, t, 3 unknowns. We cannot solve it as yet, we have to look at something. What is that something? That something is the constraint, x and y cannot be arbitrary, x square plus y square must be equal to L square, and that gives us our third equation, which is a constraint equation. X square plus y square is L square. This must be respected, otherwise these two equations will give you some solution, but you cannot solve it. Arbitrary x y. Therefore, x square plus y square must be equal to L square. This is a constraint that has to be respected. Can we do something? So we now have 3 equations and 3 unknowns. These are 3 equations and 3 unknowns, and we should be able to solve it, but it is a little tricky to solve, because now we have differential equations and an algebraic equation. We can do something better than this. What we do is we start differentiating the constraint till I get x double dot and y double dot. I differentiate once, I get x x dot plus y y dot equal to 0. I differentiate again, I differentiate the constraint again, and I get these terms x x double dot plus y y double dot plus x dot square plus y dot square is equal to 0. Now, what do? I solve for, I have this x double dot and y double dot sitting there in equation 1 and 2. I can make a substitution in the fourth equation and solve for tension. Now, tension comes out in terms of x dot square, y dot square, y, etc., which I need to solve. This is the expression of tension. I can now substitute back the tension in the equation of motion 1 and 2, and this is what I have. I substitute back this tension T in the equations of motion. Now, I have x and 2 equations in terms of only x and y. So, these are coupled equations, 2 coupled ordinary second order differential equations in x and y, which I should be able to solve. But wait, can I choose x, the initial conditions arbitrarily? Can I choose the initial conditions arbitrarily? You see, we have the constraint, so you cannot choose initial conditions arbitrarily. So, what do? These are equations of motion, 2 equations, 2 standalone equations which can be actually solved, but initial conditions x 0, y at 0, time equal to 0, x dot at time equal to 0, y dot at time equal to 0 must satisfy these constraints, our constraint, which is x at 0 square plus y at 0 square must be equal to L square, and the second is the first derivative of the constraint, which is x at 0 into x dot at 0 plus y into at 0 into y dot at 0 must be 0. Acceleration has already been taken care of. We have found t by eliminating x double dot and y double dot in double derivative of the constraint. Therefore, the double derivative will be satisfied by the equation of motion. Only thing, the 0th order derivative and first order derivative, they must satisfy these 2 conditions. Now, our choice is like this: we have 2 second order differential equations, 2 second order differential equations. Therefore, we should need 4 initial conditions: displacement at 0 and velocity at 0 for both x and y, but satisfying these 2 constraints. Therefore, the choice is actually, so we have 4 initial conditions: x 0, y 0, x dot 0, y dot 0, as required by two second order differential equations, but these initial conditions must satisfy these two constraints. Therefore, our freedom of choice is only 2. Freedom of choice of initial conditions is only 2. Suppose I choose x 0 and x dot 0, then y 0 and y dot 0 are decided, as it should be, because the pendulum, finally remember, has only one variable and we had a second order differential equations in a single variable theta. So, we cannot have more choices just because we changed our frame. So, that is the pendulum. Now, sometimes we make this approximation that the displacement x is much smaller than the length of the pendulum, and y by L is almost 1. So, y is almost not changing. In that case, you will get the tension is approximately equal to mg, because you see the pendulum is swinging, so the mass is almost moving in a straight line. So, the tension in the string is almost mg, the weight, and x is governed by x double dot plus g by L into x is 0. This is the linearized version of the pendulum equation. But this is, remember, you should remember, this is when x is much smaller than the length of the pendulum. Let us look at another example. A small block of mass m is released from rest at the point A at the top of the wedge on a frictionless free to move right angle wedge of mass capital M in a uniform gravitational field with acceleration due to gravity as g. Calculate the time taken by the block to slide down the hypotenuse of length L. So, hypotenuse of this wedge is of length L. The question is to find out the time taken by this small block to slide down from A to B. Now, this wedge, remember, can also move frictionlessly on the horizontal surface. Now, we are going to choose a convenient coordinate system. As I have mentioned, I will choose a convenient coordinate system, and I choose that x y which is fixed to the wedge. Wedge can move, wedge can accelerate. So, this x y is a non-inertial reference frame, but I must represent therefore everything as seen by an inertial observer, but using the coordinate the frame directions x y as shown. Now, there is a reason why I choose this x y frame x along the hypotenuse, because I have the length of travel along that x axis that will remain the same, and that will be very convenient. If I choose an x y which is fixed to the ground, you see this hypotenuse is moving on the ground, therefore, it will be difficult to track the particle. It can be done though, but to simplify for geometrical convenience, I have taken that x y fixed to the wedge and origin at A, the point of start. We have to find out the time taken to travel from A to B. Now, here, so first step is coordinate system, second step is to draw the free body diagram. I have shown the free body diagram of the small block. It gets the normal reaction, there is no friction, it is frictionless wedge, normal reaction and the weight. On the wedge, it is therefore only the normal reaction, and then there is weight of the wedge itself and the reaction on the wedge from the ground, no friction anywhere. Kinematics, now comes the important step of representing everything in x y, but as seen by an inertial observer. Okay. So, velocity of mass m, as I have shown here in green, velocity of that wedge capital M is the magnitude Vm times the unit vector direction represented in small x y. So, which is cos alpha I cap plus sin alpha j cap. So, that is my representation of the velocity of the wedge in x y. Velocity of the small mass is velocity of capital mass plus velocity of small mass with respect to capital mass. This we have seen, and this relative velocity v of small mass with respect to the capital mass capital M. So, velocity of the block with respect to the velocity of the wedge is very straightforward, it is v along x axis direction. So, v I cap, this is the relative velocity v I cap. That is why I mean this frame is so useful or easy to use, very convenient. So, relative velocity has become very simple, v I cap. Now, I go to acceleration. Now, acceleration I can find out by directly taking time derivative with of this velocity vector. For example, v capital M, velocity of the wedge, d dt of velocity of the wedge is acceleration of the wedge at a m, which is magnitude a m times cosine alpha I cap plus sine alpha j cap. Alpha is fixed, I cap, j cap are not changing directions, therefore, this is the acceleration. So, directly from here I get this by differentiating, and similarly I get my acceleration of small mass of the block by differentiating the velocity of the block. Straightforward algebra. These are the acceleration expressions. Now, we are ready to plug into the equations of motion. There are two mass points, one is the wedge and the other is the block. Therefore, we will have two equations of motion. Now, first one is for the wedge. Mass of the wedge times acceleration of wedge is equal to summation of all forces on the wedge. What are the forces on the wedge? The normal reaction. See, normal reaction in the block is this, by Newton's third law the normal reaction on the wedge is opposite. So, this normal reaction, and it is in the direction of minus j cap. So, minus n j cap, and then there are these two forces acting on the wedge, mg minus r in the vertical direction, which I have represented in x y frame. So, this is the equation of motion of the wedge. The equation of motion of the block, mass of the block times acceleration of the block, now all forces on the block, normal reaction in j cap direction and the weight in the vertically downwards direction. So, these are the equation of motion. I have removed the clutter, I have written only the acceleration expressions and the equations of motion that we have just now written out. Now, we have to solve, these are two vector equations, therefore, 4 scalar equations, and we have the motion of the wedge as an unknown, motion of the wedge, motion of the block as a second unknown, the reaction force R on the wedge from the ground as a third unknown, and N, which is the normal reaction between the wedge and the block, as the fourth unknown. So, 4 scalar equations, 4 unknowns I should be able to solve. The way I do it is to simplify things. What I do is I take dot product of the first equation with cos alpha I cap plus sin alpha j cap. Why does it help? Because here there is an orthogonal vector sitting, right. So, if I take dot product of the first equation with this unit vector, this mg minus r, this term drops out completely. So, immediately I have this. On the left hand side I have mass of the wedge times acceleration of the wedge, and this is here. When I take dot product with this vector, it is 1, it is the same vector actually. Therefore, I have the scalar acceleration of the wedge, mass times acceleration of wedge is minus n times sin alpha. So, I can solve for n, capital N, in terms of acceleration of the wedge. and then I plug in these expressions in the second equation, second vector equation, and I look at various components. For example, a j component. If I look at the j component, I will immediately have, so these are straightforward algebraic steps, and you can choose to do it in your own way, how you want to solve. This gives me acceleration of the wedge in terms of the mass of the block, acceleration due to gravity, this is the wedge angle alpha, mass of the wedge, mass of the block, etc. So, completely known. Therefore, I have found out the acceleration of the wedge, and then from the equation, I cap equation, looking at I cap equation on both sides of this, I will get the acceleration of the block. Now, remember, this acceleration A of the block is in that xy frame. Therefore, I have written out acceleration of the wedge and acceleration of the block in the xy frame. A, small a is the acceleration of the block in the xy frame. So, it is a relative acceleration. I can integrate this. It starts from 0 and distance travelled is L, this, and this acceleration you will find is constant. Therefore, this is our formula, and therefore, the time taken is straightforward, which I leave it to you to check. So, to summarize, we have discussed in this lecture, we have introduced Newton's laws of motion, we have introduced Newton's laws of motion, which represents a complete recipe for dynamics. I have very clearly discussed the 4 steps involved in deriving the equation of motion and solving a problem. Please try to follow these steps. The first one is setting up the coordinate system, fixing the convenient coordinate system. Second step is drawing the free body diagram. Third step is writing out the kinematics properly as seen by an inertial observer, and finally, you use the Newton's second law to write down the equation of motion, and we have looked at some problems. So, I will leave it here and close this lecture.